Hello students, welcome to the course of Data Communication and Networks. I am Dr. Munir Omar. Today in our lecture, we will study about the error correction. In the last lecture, we studied about the error detection. So now we will look into this topic. The main objectives of this is to know about the methods for error correction or the approaches which are used for error correction. And we will also study about the classifications of the algorithms used for error correction. Then we will learn about the Hamming code and understand the procedure of code word generation by using the Hamming code algorithm. So we will have one example for Hamming code and we will process that example by using the steps of Hamming code algorithm. So these are the contents for our today's lecture. First, we will revise the error and types of error, then error detection, the methods for error detection. We will have a quick look about these previous topics, and after that, we will start the error correction, the methods for error correction, and also the classification of algorithms used for error correction. Actually, there are many algorithms. We will give only the classes of these algorithms, and after that we will have Hamming code, and we will study this Hamming code in detail with an example. Now we are going to have a quick revision of error detection, which we studied in our previous lecture. First error, it is obvious that the transmission medium is not perfect. So whenever we transmit data, that data may get scrambled or may have some sort of interaction with noise. So there might be some impairments. So the data might be get corrupted, which has been transmitted by the sender, and at the receiving it, the data might be different from the sent. So that thing is referred to as an error. For reliable communication, errors must be detected and corrected. So this is obvious, and this is the need of communication systems to get the corrected data before the processing of data. So these are performed, the error detection and correction are performed at data link layer and transport layer. Data can be corrupted during transmission, and most of the applications require that errors be detected and corrected. Two types of errors: single bit error and burst error. In single bit error, we say that there is only one bit which has been changed or which has been corrupted, and that is different at both the sides, the sender side and the receiver side. So this is known as single bit error. Only one bit at any place is changed. So then we have burst error. Burst error means that there are more than one bits, and these are not consecutive, and the length of burst error is measured as the starting bit and the ending bit. More than one bits then may not consecutive, and the third thing is the length should be measured from starting corrupted bit until the last corrupted. So this is the length of this error. Then error detection. Error detection codes are used. These are actually some additional data which is attached with the original data, and this additional data is used to help us detect the error in the original data. So this slide shows the concept of encoder and decoder. Actually, we need redundant bits or some additional bits to be attached with message. So for the generation of these redundant bits, we use a generator, and that generator is applied on the message. At receiving end, the same procedure is applied, and here the checker is used instead of generator, and this checker uses the same algorithm or the same method adopted by this generator to verify the status of data, whether it is correct or not, whether it is according to the sent data or not. So we need redundant data. The simplest way is to send two copies of data, but that thing would double the transmission time, and also the computation time will be slower as compared to normal case. So we can add some additional information with the message to help the receiver detect the errors in the data. Shorter group of bits may be added with to each packet. These these additional bits are used by the receiving device to detect whether there is any error or not, and once the process is done, these additional bits are discarded by the receiver. So here we have data. Some additional bits are generated by a function, and these bits are appended with the actual data and sent. So with the help of these bits, the receiver check the status of the received bits and decide whether to accept or to reject. There are four types of redundancy checks. The first one is VRC, second one is LRC, then CRC, and checksum. For VRC, CRC, we use parity bit. Parity bit is an additional bit to be attached with the data to make the number of ones either even or odd. So if we need even parity, and most of the systems even parity is needed, so for that purpose one additional bit is added with the original data, and the value of that bit is decided by the number of ones in the data. Now here we have 1 2 3 4 5, we have 5 ones, so this is odd number of ones, so we must make it even by providing the parity bit equal to 1. So now here in this entire block we have even number of ones, so this is even parity. Error correction. The simplest way for error correction is to inform the sender about the status of transmitted packets, about the detected error, and ask to retransmit the data. So if the error is detected in the received packet, then the sender can be informed about the detected error and can be requested to retransmit that data. This is very useful method and very common in most of the data communication systems, but somehow it is costly because if the medium is highly prone to potential errors, then such type of requests for retransmission would be very high and the bandwidth will be lost on the retransmission of data. Then the best way to detect the error and then correct it at the receiver's end without acknowledging or informing the sender. The sender forwards the error correction code to the receiver along with the data. It is just like error detection, as we saw that with data some additional bits were sent for the detection of errors. So in the same manner, for error correction some additional bits or additional data is appended with the original data and transmitted towards the receiver. The receiver uses that appended data or the additional data or the code to automatically detect and correct the error. This type of error correction is more sophisticated than error detection, and also this procedure is more sophisticated than asking the sender for retransmission of data. To correct the error in data frame, the receiver must know exactly which bit in the frame is corrupt. To locate the bit in error, redundant bits are used as parity bits for error detection. So, before correction of bits, it is essential to know the corrupted bits, and for detection of corrupted bits, parity bits are used. There are two approaches for error correction. The first one is backward error correction, and the second one is forward error correction. So, we will discuss these two now in the coming slides. Backward error correction. This is the first approach we saw here. This approach is also known automatic repeat request ARR. The receiver device sends a request to the source device to resend the data after detecting the error or errors in the received data. More often used because it requires less bandwidth. But remember, if there are less chances of error, then it would require less bandwidth. But if the chances are higher, then it would require more bandwidth. A return channel is needed for backward error correction. So there must be some sort of mechanism so that the receiver also send the information about the received data to the sender. So for that purpose, the backward channel is also required. There are two ways for backward error correction. The first one is positive acknowledgement, and the second one is negative acknowledgement. In positive acknowledgement, the receiver returns confirmation of each block received correctly. The transmitter resends the block if that is not acknowledged. We have already studied about the acknowledgement, which is performed by TCP at transport layer. Then we have negative acknowledgement. The receiver returns a request to retransmit only the data with error. So, if the receiver detects an error, then it informs the sender. Otherwise, for correct data, no acknowledgement is sent, or the sender is not informed about the correctness of received data. Then we have forward error correction. This technique allows the receiver to detect and correct errors without asking the sender for retransmission. The correction is made at the receiver's end, and for the correction, there is no involvement of sender. However, the sender adds some additional data with the original data before the transmission, and that additional data is used for detection and correction. The bandwidth requirement is higher, but return channel is not needed. If there is less potential, if there is less chances of error, or the medium is not at the worst condition, then the bandwidth requirement would be uh, higher as compared to the backward error correction. But the return channel for acknowledgement or for the information about the delivery would not be needed for the receiver. Redundant data sent by transmitter is also called error correction code. The additional data which is appended with the original data, that data, as we know, is called redundant data, but for error correction we call that data error correction code. In the process of error correction, some predetermined procedures are adopted by the sender and receiver, and this predetermined procedure is used to design the redundant bits, to design or calculate these redundant bits. And these redundant bits are added to the transmitted information, or the information which has been transmitted from sender to receiver. Each single bit in these redundant bits will have some importance, and that single bit may have a function of many parts of the original data. Means that suppose we are adding 4 bits with the original data, so one single bit may affect multiple bits in the original data. So, backward error correction, the correction by retransmission of data. When the receiver detects an error in the data received, it requests back the sender to retransmit the data unit. Forward error correction at the receiving end without retransmission of data from the sender. When the receiver detects some error in the data received, it executes error correcting code which helps it to auto recover and to correct some kinds of errors. There are two main categories for the error correction algorithms. These are block coding and convolutional coding. In block coding, we have an example that is Hamming code, and for convolutional coding, we have Viterbi algorithm. Block coding works on fixed sized packets of bits. like 8 bits, 16 bits, 13 bits, 11 bits. So there would be a fixed size, a fixed number of bits in a block for block coding. In the convolutional coding, there is no fixed size blocks. The sizes may vary from time to time or from different senders. The message comprises of data streams of arbitrary length, and a sequence of output bits are generated by the sliding application of Boolean functions to the data stream. So, in this mechanism, the algorithm deals with a stream of bits, and that stream would have an arbitrary length of bits or variable length or random length of bits, and the sliding application generates the error correction codes continuously. Now let's start the Hamming code. In Hamming code, we provide some additional bits. These bits are known as parity bits, and we specify some particular places for the parity or the redundant bits in the block. And with the help of these bits, we detect and correct the errors in the transmitted or the received data at the receiving end. So if we look into this block here, we have 4 bits received, and with these 4 bits we have three redundant bits or parity bits. So with the help of these 3 bits, we can judge the status of these 4 data bits, and if there exists in any if there exists any error, then that error can be corrected with the help of these bits. Hamming code is a linear error correcting code named after its inventor, Richard Hamming. Hamming codes can detect up to 2-bit errors and correct single bit errors. We will see that how the detection and correction take place by having an example. This method of error correction is best suited for situations in which randomly occurring errors are likely, not for errors that come in burst. Hamming code can be applied to any length of data to find and correct errors. So, for each length, we will have a particular number of redundant bits. It doesn't mean that for all lengths there would be a single set of additional bits. So these are the steps for calculating the Hamming code. Step number 1, calculation of the number of redundant bits. So we must calculate the number of parity bits for the given data bits. Number 2, positioning the redundant bits. So where these redundant bits should be placed in the data which is provided. Number 3, the step number 3, calculating the values of each redundant bit. Then what should be the value of parity bit or redundant bit which is placed in the data bits, in between the data bits. I'm quickly clarifying these 3 steps with an example. So the first step is to know the number of redundant bits. So how many parity bits are required? If we have, let's say we have 4 bits provided. So for this we will calculate and we will get 3. And if there are 5 bits, then these redundant bits would not be 3, it would be 4. Let's say for 8 bits it would be different. So we will know the number of redundant bits in the first step. Then the second step is about the placement. So where these bits should be placed. So we are placing these bits at number 1, at number 2, and at number 4 if we have 4 data bits. Then the third step is that what would be the values of these three bits. Here we would have some value, like here we have some values given. So for these redundant bits r1, r2 and r3, what would we should give either 0 or 1 to adjust the parity values according to our requirement. So now we are starting with step number 1 in details. If the message contains m number of bits, the data bits, and r number of redundant bits are added. The m can be 4, 5, 6, 8, 16, 32, any number of data bits. So we must add some additional bits